Welcome to Lesson 3-5, Proving Segment Relationships. By the end of this lesson, you should be able to prove theorems about line segments. Here are the postulates on points, lines, and planes. We've covered these 7 early on, so anything that you're not familiar with or not necessarily familiar with, but that you don't recall, please take a moment to write them down. You can pause the video, do as you need. Here are our newer postulates and theorems. So first we have the ruler postulate. The points on any line or line segment can be put into one-to-one correspondence with real numbers. For example, given any 2 points A and B on a line, if point A corresponds to 0, then point B corresponds to a positive real number because it's on the right side of the ruler, right? And any ruler only measures in positive numbers. The segment addition postulates. If points A, B, and C are collinear, then point B is between points A and C if and only if the length of AB plus the length of BC is equal to the length of AC, as can be seen in this diagram. Next, we have our properties of segment congruence. We have the reflexive property of congruence, which states line segment AB is congruent to line segment AB. The symmetric property of congruence, which states that line segment AB is congruent to CD, then line segment CD is congruent to line segment AB. Last, we have the transitive property of congruence, which states if line segment AB is congruent to line segment CD and line segment CD is congruent to line segment EF, then line segment AB is congruent to line segment EF. These are the properties of equalities. These we'll also be using. Please pause the video and write down anything that you have not memorized, and write them a few times. You need to study to be sure you remember them. Okay, here we have an example. This is the segment addition postulate. It says write a 2-column proof given that line segment QT is congruent to line segment RV. Prove that line segment QR is congruent to line segment TV. Of course, what appears first? The given. Remember, I said that almost 90% of the time, your given will be the first statement and reason. What's given and the reason is given. Let's take a look at what comes next. They tell us that the reason is definition of a congruence. So remember, the definition of congruence says that if 2 line segments are congruent, it's because their lengths are equal. So that means that we're saying QT must be equal to RV, as seen in the box where we have the possible statements and reasons. QT is equal to RV. So now that we know that QT is equal to RV, we can say that QR plus RT is equal to, QR plus RT is equal to QT, right? QR plus RT is equal to QT, and RT plus TV is equal to RV. This is because of our segment addition postulate. We're adding the 2 segments. Remember earlier in the year, the 2 parts make up the whole. So from there, what can we say? Well, we know QT is equal to RV, so I believe we're going to do a little substitution because QT is equal to RV. That means that QR plus RT must be equal to RT plus TV. And how is this possible? Because we substituted the values of QT and RV in this situation. This is the substitution property of equality. Next, what do I see happening? They told us subtraction property of equality because we're subtracting RT from each side of the equation, and that would leave us with QR equals TV. So what allows us to go from this line to this one? Well, we actually subtracted, so we're now substituting it with its known value. So that was the substitution property of equality. And now we can say that line segment QR is congruent to line segment TV by the definition of congruence, because we're saying that if two lengths are equal, two lengths of two segments are equal, then the two line segments are congruent. Okay, so here we're going to do the example one check. I'm definitely going to need you to pause the video and try it on your own. So pause and then I'll resume, and then you can resume at any time. All right, complete the two-column proof. Two intersecting lines determine a plane. Given line segment CE is congruent to FE and line segment ED is congruent to line segment EG, prove that line segment CD is congruent to line segment FG. So what is our almost always our first reason? It's not in the boxes here because we should know it by now. It is given. The first reason is given. Next, how are we able to go from saying that line segment CE is congruent to line segment FE to saying that their lengths are equal? We're going from saying line segment ED is congruent to line segment EG to saying that their lengths are equal. Of course, that's our segment addition. That's our definition of congruence. Definition of congruence. So we're going from saying they're congruent to equal, congruent to equal. We can also go backwards, saying the lengths are equal to the segments are congruent. So the next one, CE plus ED equals CD. CE plus ED equals CD. So the two parts equal the whole. Well, of course, that's our segment addition postulate. Now let's take a look at the next one. I notice CD stays the same, but CE is changed to FE, ED is changed to EG. Well, CE is equal to FE, so that allowed us to substitute. And so this is the substitution property of equality. Next, we have FE plus EG equals FG. FE plus EG equals FG. Well, that's the two parts equal to the whole. So that means segment addition postulates. Next, we see CD equals FG. I see FE plus EG equals CD and FE plus EG equals FG. So these two must be congruent, and that is substitution, because I'm substituting FE plus EG with CD. So CD equals FG. And now we're going from saying that these two lengths are equal to saying their two line segments are congruent. That is the definition of congruence. All right, hopefully you had that one correct. Let's look at example 2, prove segment congruence. Write a two-column proof. If you're given R is the midpoint of QS and T is the midpoint of VS, and then you're given QR is congruent to VT, prove that RS is congruent to line segment RS is congruent to line segment VS. So the first reason they've already given is the given. It says R is the midpoint of QS, T is the midpoint of VS, and of course that is given. How can we then say that line segment QR is congruent to line segment RS and line segment VT is congruent to line segment TS? If you remember from a previous lesson, we were able to say it through the midpoint theorem. The midpoint theorem allows us to say that if you're the midpoint, then the two segments are congruent. The next line is given. It says line segment QR is congruent to line segment VT. Now, how can we go from these two statements to the fourth one? We're going from saying QR is congruent to VT to QR is congruent to TS. Well, if we see here, VT is congruent to TS. So line segment VT is congruent to line segment TS. And so therefore, where I had line segment VT, I can now place line segment TS. That is our transitive property of congruence. Because QR is congruent to VT, VT is congruent to TS, so I can go and say QR is congruent to TS. Now, this time we have to come up with the next statement. What are we looking for here? We're trying to get to line segment RS is congruent to line segment TS, and they want us to use the symmetric property of congruence. So we're saying that RS, line segment RS, is congruent to line segment QR. So line segment RS, through the symmetric property of congruence, is congruent to line segment QR. And here it is here. We just flip them around. And so the next one would be the transitive property of congruence. And so now we're going from saying QR is to RS and QR is to TS to RS is congruent to TS. That is the transitive property of congruence. All right, you try the example 2 check on prove segment congruence. Pause the video, try it on your own. Of course, there's a box with your statements and reasons. Pause the video. Okay, so here we have K is the midpoint of line segment GJ, and H is the midpoint of line segment GI. And guys, as we can see, that is in our given, and so that is its reason. They're only asking us to find a few lines, so let's go through the process. You already know line segment GJ is congruent to line segment GI. And K is the midpoint here, and H is the midpoint here. So according to the midpoint theorem, then we can say the line segment GK is congruent to line segment KJ. GK is congruent to KJ. And then line segment GH is congruent to line segment HI. That's the midpoint theorem. Now, through the definition of congruence, we can say that those segments have equal lengths. So GK is equal to KJ and GH is equal to HI. Next, how can we say that GJ is congruent to GI? Looking at your choices, you have the midpoint theorem, you have RS is congruent to QR, segment addition postulate, and definition of congruence. Well, our reason here is given. It's sitting right there. It is given. Next, it says definition of congruence. What can we say here? What is congruent here? And I realize we have a little error in the box. That's not it. But if we're going from line segment GJ is congruent to GI, then we would have to say GJ is equal to GI. That is the definition of congruence. Next, number 6. Now that we've said that those are equal, and we have another line up here about GK equals KJ and GH equals HI. Let's take a look at what we're going to go to here. We have GJ equals GK plus KJ. GJ equals GK plus KJ. Wow, that looks like the segment addition postulate. And GI is equal to GH plus HI. Again, that looks like the segment addition postulate. From there, they're using the substitution property of equality. Because we know GJ and JI are equal from line 5, then we can put what they're equal to each other by substituting. And then we can substitute again because we know that GK and KJ are equal. I can substitute and I'd have two GKs, GK plus GK equals GH plus GH because GH is equal to HI. So they substitute it one more time here and here. Next, we're adding. You add GK plus GK gives you 2 GKs. GH plus GH gives us 2 GHs. So dividing by 2 on each side, division property of equality, you end up with GK equals GH And of course, if two lengths are equal, then their segments are congruent, and that is the segment addition. I'm sorry, that is the definition of congruence. Definition of congruence. Hopefully you had that all right. The only thing that probably tripped you up was number 5. There was an error there. All right, so let's learn a little bit. We have two-column proofs and flow proofs that are considered formal proofs. A formal proof is a logical argument that includes all the steps and corresponding justifications needed to prove a relationship. An informal proof is a simplified proof that summarizes the logical reasoning used to provide a relationship. In an informal proof, some steps that are considered obvious may be skipped, and some reasons or justifications may be omitted. A narrative proof is a type of informal proof that can contain bullet points, lists, calculations, or paragraphs. Let's look at, I believe, this last example, number 3. It's on determining congruence, and they're using planning. Marcellus is planning a birthday party. He measured a length of ribbon for a balloon and then uses this ribbon to measure and cut a second ribbon. He continues this pattern of using the last ribbon that he cut to measure the next ribbon until 10 ribbons have been cut for balloons. Is the last ribbon that he cut the same length as the first ribbon? Justify your argument by using a narrative proof. So let's think about it. The answer is yes, because the first ribbon is the same length as the second ribbon, and the third ribbon is the same length as the second ribbon. The first ribbon is the same length as the third ribbon by what? What property allows us to say that these would be congruent? It's the transitive property of congruence. And this logic can be applied until the last ribbon is shown to be the same length as the first ribbon. Now you have an example 3 check. Determine congruence. Maria is 11 inches shorter than her sister Clara. Luna is 11 inches shorter than her brother Chad. If Maria is shorter than Luna, how do you know the heights of Clara and Chad compare? What else can be concluded if Maria and Luna are the same height? Now, I wrote this out and I didn't mean for you to see it so early, but it's there. If Maria equals Clara's height minus 11 inches and Luna equals Chad's height minus 11 inches. So these two, and just trying to separate, these are two situations. Maria is Clara minus 11 and Luna equals Chad minus 11. And if Maria is shorter than Luna, then Clara's height minus 11 inches is less than Chad's height minus 11 inches. Seeing as they both have 11 inches, if I add 11 inches to each side, I'm left with Clara has to be less than Chad in height. And that really helped the situation because it can be concluded that Chad and Clara are the same height if Maria and Luna are the same height. Then Clara and Chad are also the same height. So remember the question, if Maria is shorter than Luna, how do the heights of Clara and Chad compare? Well, we said Clara would be shorter than Chad. But what else can be concluded if Maria and Luna are the same heights? Well, it can be concluded that Chad and Clara are the same heights if Maria and Luna are the same heights. All right, let's move forward. Now we have your mini assessment. Try to do this one on your own. Of course, we'll look at it when we get back to class. Your assignment following this lesson is going to be to complete lesson 3-5 in McGraw-Hill. Thank you. So don't forget lesson 3-5, proving segment relationships in McGraw-Hill.